Hello and welcome to another NGen Math 8 lesson by eMath Instruction. My name is Kirk Weiler and today we're going to be doing Unit 8, Lesson 1 on the Pythagorean Theorem. Now it's not often in math that you run across ideas or formulas or things like that that literally are tagged with a person's name. But there was this guy named Pythagoras and he lived thousands of years ago. And this formula that he came up with, known as the Pythagorean Theorem, is one of the most useful formulas in all of math, which is why we're going to devote an entire unit to it. Unit 8 is just on this single formula. Isn't that amazing? It's like an entire unit using like the area formula of a triangle and nothing else. Anyway, so today what we're going to be doing is developing the formula and using it a bit, and then throughout this unit you'll get more and more work with it. It is a formula that on occasion you want to have your calculator for, so make sure you have your scientific calculator available to you in this lesson. And let's get right into it and figure out what the Pythagorean Theorem tells us. All right, here we go. Now the Pythagorean Theorem specifically relates the lengths of the three sides of a right triangle. A right triangle, not a generic triangle, but a triangle that's got a right angle in it. It is one of the most important ideas in all of geometry. So let's get into it a bit. Okay, let me try to get exercise 1 to the top. Let's take a look at exercise number 1. In the right triangle below, the two legs have been given the variable names a and b. The hypotenuse has been given the name c. Let's talk about this a little bit before we even get into measurements, all right? In every right triangle, right, there are the two sides that are perpendicular to each other, the two sides that form a right angle, and those are known as the legs of the right triangle. Then there is the side that is opposite of the right angle. Literally, if you took the right angle and drew an arrow pointing at the opposite side, that's known as the hypotenuse. The hypotenuse is the longest side in a right triangle. So you've got the two legs, and we're going to call them A and B, that just is their lengths, and then C is the length of the hypotenuse. So let's see what exercise 1 asks us to do. Letter A, measure each of these lengths in centimeters. They should all be whole numbers. If not, round to the nearest centimeter. Write on your diagram and below. All right, excellent. So take your ruler in centimeters, measure out the length of A, write it here, measure out the length of B, write it here, C, etc. Pause the video now and go ahead and measure these lengths. All right, let's do it. So simple enough, right? For side A, it appears that it's got a length of 8 centimeters. All right, so let me put down 8 centimeters right here. We'll label them on the diagram eventually. Side B, I can make that pretty easy by just kind of rotating it up. That looks like it's got a length of 6 centimeters. And finally, if we take a look, if we can get our ruler to behave, and we take a look at side C, it's got a length of 10 centimeters. There we go. All right, so it's got a length of 10 centimeters. Let's get those all drawn on the diagram. We've got 8 centimeters. I gotta turn a little bit sideways, 6 centimeters and 10 centimeters. All right. Now, let's take a look at letter B. Find the value of the following expression for the values above. Show your substitutions. Okay, so very clearly, all I want you to do is figure out the value of a squared, a to the second, plus b to the second, when a is 8 centimeters and b is 6 centimeters. So just throw those two numbers into this formula and see what you get when you evaluate the expression. All right, well, again, it's simple enough, right? A was 8 centimeters, so b was 6 centimeters. 8 squared is 8 times 8, which is 64. 6 times 6 is 36. And 64 plus 36 is 100. All right. Now, the final piece, and this is important, right? Letter C asks us, how does the value in B, that 100, how does that relate to the value of C? So the question is, do you see any connection between the value of C and this answer right here, 100? Pause the video now and think about that a bit, especially in the context of this expression that we evaluated right here. Well, given that we got this expression by taking one leg and squaring it, the other leg and squaring it, and adding them together, hopefully you notice that that 100 is simply the 10 squared. All right? So in other words, 10 squared equals 100. All right? And that's the relationship. The fascinating thing is that that relationship is always true in a right triangle. In a right triangle, if I take one leg and I square it, the other leg and I square it, and I add them together, I will always get the square of the hypotenuse. Always. Now, we haven't proved that. In fact, we're going to wait until the absolute last lesson of this unit to prove it, but that is the Pythagorean theorem. Let's summarize that. All right, the Pythagorean theorem. Let me get all this stuff out of the way so you can actually see our nice little diagram there. The Pythagorean theorem, named after Pythagoras, you know, that like thousands of years ago they only had one name, and then now it seems like the same way with famous people. But if the lengths of the legs of a right triangle are given by A and B, all right, and the length of the hypotenuse is given by C, then the following equation is always true. A squared plus B squared equals C squared. Or leg 1 squared plus leg 2 squared equals the hypotenuse squared. All right? Always, always, always. Now, what this theorem allows us to do, and we're going to do this in a moment, is anytime you know two sides of a right triangle, you can use this theorem to find the third side. And it is shocking how often that is helpful in math problems and in problems in the real world. Engineering problems, physics problems, all sorts of things. Very often you will know two parts of a right triangle and you'll want to find the third part. So let's see how that's done in a very straightforward exercise. Let's take a look at exercise number 2. A right triangle has legs with lengths 5 inches and 12 inches. Use the Pythagorean theorem to find the length of its hypotenuse. All right, so let's take this real slow on our first time and maybe even throughout this entire lesson. So, you know, whenever we have a right triangle, we like to think about the legs in terms of these A and B. All right, so I'm going to say A is 12 inches and B is 5 inches. Now, it doesn't matter at all which one of these is A and which one of them is B. That's irrelevant. The hypotenuse has to be C. All right, the side that is opposite of the right angle, right, the side that is opposite of the right angle, that has to be C. Now, the Pythagorean theorem tells me that if I take A and I square it, take B and I square it, and I add them together, I will get the square of the hypotenuse. So let's substitute the known numbers that we have now for A and B into this formula and see how we can figure out the value of C. All right, so here we go. For A, I'm going to put in 12. For B, I'm going to put in 5. All right, and I'm trying to figure out C. We'll leave that just as C for right now. Now, hopefully you know that 12 squared is 144, but if you don't, do that on your calculator. 5 squared, that certainly you should know, is 25. All right, now I can do 144 plus 25, and I'll get 169 equals C squared. And let's pause for a second. Because whenever we use the Pythagorean theorem to solve for a missing side, we will always eventually get something that looks like this. And when I say something that looks like this, what I mean is that you'll have one of the sides that's missing, squared, equals a number. C squared equals a number, A squared equals a number, B squared equals a number, whatever. Now, in the last unit, we worked with exponents and roots. And we solved some equations that looked like this. Often the variable was x, but whatever. The plain fact is, when I'm looking for a number whose square is 169, that means that the number I'm looking for must be the square root of 169, right? So this is automatic. If C squared is 169, then C is the square root of 169. Now, if you don't know what the square root of 169 is off the top of your head, then that's where it's really, really quite helpful to just have your calculator, right? I throw in the square root symbol. I put in 169, and C is 13. And that's it. Now, specifically in this case, I should be good about my units. C specifically is 13 inches. Now that is the absolute most straightforward way that we can use the Pythagorean theorem. In other words, I know the two leg lengths, I square them both, 12 squared, 5 squared, 144 and 25, and of course if you don't know these, please do them on your calculator. In fact, you could do this entire expression all at once. You could actually take this thing and just do 12 squared plus 5 squared, right? And you can get your 169 that way. So you could actually do the a squared plus b squared all at once on your calculator to figure out what c squared is, but then you have to take the square root of that number to get that missing hypotenuse. So let's do that a little bit more, all right? The most straightforward application of the Pythagorean theorem involves finding the hypotenuse, the longest side, when we know the two leg lengths. Now sometimes, right, sometimes that hypotenuse is not going to be as nice as it was last time. Last time the hypotenuse turned out to be 13 inches. But sometimes when we take the square root of a number, we get an irrational answer, right? One whose decimal goes on forever, remember, without repeating or terminating or anything like that. And that actually happens more often than the nice ones happen. Okay, but we're going to always have kind of a mix. Sometimes our answers are going to be nice rational whole number answers like we had last time, 13. And sometimes they're going to be a bit uglier. They're going to be these irrational numbers that maybe we have to round. So let's take a look at exercise number 3. For each right triangle below, find the length of the hypotenuse using the Pythagorean theorem. If the length is irrational, round to the nearest tenth. All right, well what I'd like you to do is I'd like you to try to do what we just did in the last problem on letter A. I'd like you to take your 12, square it, your 9, square it, add them together, get that sum, then find its square root to figure out the value of C. Now, if it turns out to be irrational, and you'll know because when you take that square root, if you've got some kind of messy decimal answer that goes on forever without repeating or terminating or whatever, just round it to the nearest tenth. On the other hand, if it's a nice number, just put down that nice number. Pause the video now and see what you can do on letter A. And again, I'm going to call this A, I'm going to call that B. It doesn't matter which one we call A and which one we call B. It does matter which one we call C. All right, so let's do it. I'm going to have my Pythagorean theorem, a squared plus b squared equals c squared. All right, a squared, 12 squared. Then 9 squared equals c squared. All right, 12 squared is 144. 9 squared is 81. All right, at some point in time, at any point in time that you feel like you need your calculator to help you with the arithmetic, do it. That's not really the point right now, right? The point isn't the arithmetic. So we get c squared is equal to 225. Again, every time when you do a Pythagorean theorem problem, you're going to get to a point where you have either a squared equals a number, b squared equals a number, or c squared equals a number. And the way you always undo squaring is with square roots. In fact, some teachers will throw this step in because the square root of c squared is definitely c. Let me just extend the page a little bit so we've got a little more room. And now let me do the square root of 225 on my calculator. This one's going to turn out nice, I hope you found. And we end up having 15 inches. All right. So in that one, right, our answer is a nice rational number, right? It's in fact a nice whole number, okay? And that'll oftentimes be the case, not always. Now let's take a look at one where the answer turns out to be an irrational number. So what I'd like you to do is pause the video now, work through letter B. This time the answer is not going to be a nice whole number. You're going to have to round it to the nearest tenth, but see what you get. All right, let me move this a little bit out of the way. Again, I'm going to let my A be equal to 10, my B be equal to 8. So I'll have my C is the missing. So A squared plus B squared equals C squared. That's going to be 10 squared plus 8 squared is equal to c squared. 10 squared is 100. 8 squared is 64. C squared, that'll give me c squared equals 164. So now I'm going to take the square root of both sides, And let's see what the square root of 164 is. Let me just do something really quick. Let me make this a little bit, I guess that's already as big as it's going to get. All right, so the square root of 164. 164 is not a perfect square, so we get this messier answer, and rounded to the nearest tenth, we'd get 12.8 centimeters. All right. But notice, it's the same thing that we do each time. I take this, I square it. I take this, I square it. I add them together. I get a result, right? I take the square root, and I have my hypotenuse. Now, that's the most straightforward thing that we can do with the Pythagorean theorem. Where it gets a little more challenging is if we know one of the legs and the hypotenuse, and we're looking for the other leg. So let's talk about that a bit. All right? Sometimes we use the Pythagorean theorem to find the length of the missing leg of a triangle. This involves just a tiny bit more algebra, and I'm telling you, just one additional step. So let's take a look at exercise 4. Let me bring this up to the top and see how that works. For each right triangle shown below, use the Pythagorean theorem to find the missing leg length. If the answer is irrational, round the length to the nearest tenth. All right, so notice in letter A, right, we know the hypotenuse this time, right? We know the side that's opposite the right angle, and that one we have to call C. Now, am I missing A or am I missing B? It just doesn't matter. Almost always, if I'm solving for a missing leg length, I'll just call that missing leg length A. Again, it doesn't really matter, but I call it A just because the A comes first, right? So I'm going to say A is the one I don't know, and I'll say that the 8 feet is equal to the B. All right, so now let's see how it works out with the Pythagorean theorem. Okay, I'm going to write down the Pythagorean theorem again. A squared plus B squared is equal to C squared. Okay, now I don't know A squared, so I'm going to just leave it like that. B is now 8, so I'm going to have that there, and C is 17. All right, again, A squared is what I'm solving for, so I'm just going to leave it like that. 8 squared is 64, and I don't have 17 squared memorized, so I'm going to just do that in my calculator. 17 squared is 289. Now, let's pause for a minute and talk about this, because this is where it gets a little different than before, right? Before at this stage, I literally had C squared equals a number, and I took the square root. Here I have A squared plus 64 is equal to a number. So here's the one additional step when we're solving for a missing leg instead of solving for the hypotenuse. We simply have to subtract this 64 from both sides. We've got to isolate the A squared or the B squared, right? When we're solving for the hypotenuse, the C squared is by itself anyway, right? It's not, there's no other letters with it. But here, for either A or B, we've got to get rid of this 64. So I'm going to subtract a 64 from both sides. And again, I could do that on my calculator, or I could just do it in my head. At least in this case, I can do it in my head. And I'll get A squared is equal to 225. All right, and now I take the square root. All right, so the only additional step is throwing in that subtraction. And then I do the same thing I did before. I take the square root of 225, and I find that A must be 15 feet. All right, so again, just to be clear, the only difference between finding a leg versus finding the hypotenuse is that we'll have to do this extra step where we isolate the square of the leg length before we take the square root. All right, try that in letter B. All right, let me get this over here. All right, I'm going to again let this be equal to B. I'm going to let A be the one I don't know. I'll put a little question mark there. C is equal to 20. So I'm going to have A squared plus B squared equals C squared. I don't know A squared. B is 14. C is 20. All right, 14 squared is one that sometimes I remember and sometimes I don't, and that means I like to check it. I think it's 196, yep. 20 squared, that's not so bad. Now I've got to subtract that 196 from both sides. All right, that'll leave me with a squared equals 400 minus 196, 204. And now I'm going to take the square root of 204. Let's do that. The square root of 204 gives me 14.3, let's say rounded to the nearest tenth. All right. Now, believe it or not, as we go through this unit, and this whole unit is just the Pythagorean theorem. That's all it is. It's just the Pythagorean theorem again and again and again, applied, various things, right? As we go through the unit, really, when we use the Pythagorean theorem, we're only going to do one of two things. We're either going to be solving for the hypotenuse, or we're going to be solving for one of the leg lengths. That's it. That's its entire purpose. And the two procedures are very, very similar. The one big difference being that when you solve for one of the leg lengths, you will have to do a subtraction in order to get rid of the square of the other leg length, in order to isolate the missing side that we're trying to find. When we're solving for a leg, we'll have to do that subtraction. When you're solving for the hypotenuse, it's actually quite easy because the hypotenuse is already all by itself. All right, let's keep going. Now, the Pythagorean theorem is such an important tool. It's because it shows up in geometry all the time, because there's just so many shapes that have right angles in them. And sometimes it shows up even when you're not kind of like expecting it to. So let's take a look as our last problem at number 5. Both squares and rectangles have right angles. If we draw in diagonals, they create two identical right triangles. Which of the following figures has a longer diagonal? All right, so this is a classic case of where the Pythagorean theorem can be useful in order to find something even when it doesn't appear that right triangles exist. So in this square, right, if I want to think about its diagonal, I will draw it in like that. And as soon as I draw that diagonal in and I label it, right, and maybe I shouldn't have labeled it right away with C, but I did, right, we can see the right triangle. All right, I know that's a fairly poorly drawn diagonal, but you get the picture, right? And in fact, what we're missing is we're missing the hypotenuse. So let's figure out the length of that diagonal together, and then maybe we'll have you do this one on your own. Now again, in this case, what we're missing is the hypotenuse, which is why I labeled it C, but it's also the side that's opposite the right angle. So I've got my a squared plus b squared equals c squared. It doesn't really matter which one I call which in this case. So I'll have 5 squared plus 5 squared is equal to c squared. 5 squared is 25, another 5 squared is 25, equal to c squared. And eventually I'll have c squared is equal to 50. I wish 50 was a nice perfect square. It feels like it should be, but it's not. So remember, all I'm really trying to do is figure out which one's got the longer diagonal. They didn't really say to round to any amount here, but maybe we'll just round to one decimal place and say 7.1 inches. Again, by comparison purposes, that should probably be good enough. Now what I'd like you to do is do the same for that rectangle, draw in its diagonal, throw in a right angle where you know one is, and then figure out the length of its diagonal. Pause the video now. All right, so our diagonal, and it doesn't really matter which diagonal we draw in, they're the same. Again, here's our right angle. The thing that we're missing is, again, the hypotenuse, so we'll call it C, okay? Now I'll call one of those A and one of them B. It doesn't matter which, we'll go A here and B here. So I'm going to say A squared plus B squared is equal to C squared. 3 squared plus 7 squared is equal to C squared. That's going to be 9 plus 49 is equal to C squared. And C squared is equal to 58. Now, we'll finish this off in just a moment, but strangely enough, this is enough to really tell us that this diagonal is going to be longer than this one. You see, here C squared was equal to 50, and here C squared is equal to 58. The plain fact is if I take the square root of 58, that's going to be larger than the square root of 50, just by default. That's the way square roots work. But let's finish it off, right? So c is going to be the square root of 58. Again, this is going to be kind of an ugly answer. Given that 58 is not a perfect square, it's going to be an irrational answer. So we'll have to round it. But that's going to be 7.6 if I round it to the same accuracy level, inches. And therefore, we can say that the rectangle has a longer diagonal than the square. All right. And again, by using the Pythagorean theorem. In fact, before this lesson, there was really no way for you to even be able to figure out the lengths of those diagonals, other than, like, let's say, taking a ruler out. But the Pythagorean theorem allows us to find them because we can create right triangles where that diagonal is the hypotenuse. And then we know the two leg lengths. All right, let's wrap this up. Okay, today you got exposed to one of the most important ideas in all of mathematics. So important that it got tagged with a guy's name who has been dead for about 3,000 years. I mean, seriously, this thing is an old theorem. But because of how important right triangles are in the real world, half of a square, half of a rectangle, all sorts of places where right triangles come up, the Pythagorean theorem is an amazingly important theorem. It will always allow us, given that we know two sides of a right triangle, it will always allow us to find the third side. Now, what we saw today was that's particularly easy when the thing that we're missing is the hypotenuse, the longest side of the right triangle, the one that's opposite the right angle, okay? But it can also be used to find a missing leg length with just a little bit additional algebra. Now, key in all of this, of course, is understanding that when we have an equation that looks like a variable squared equal to a number, we solve that by finding the square root of that number, right? And that's what we saw right there at the last bit of the last unit on exponents and roots. All right, well, you're going to get plenty of practice with the Pythagorean theorem in the homework, obviously, and in every other lesson in this unit. For now, I just want to thank you for joining me for another NGen Math 8 lesson by eMath Instruction. My name is Kirk Weiler, and until next time, keep thinking and keep solving problems.